So is it visible? The screen is visible?
Yes, sir.
Okay, thank you. So as you know, in the last class we were looking at big O notation. So I'll just again write down the definition and give you a couple of more examples, right? So remember, if f and g are two functions, normally we take f and g to be a positive functions, but in general also we can define. So these are functions from set of integers or reals to reals. Okay, then we say that f of x is big O of g of x. This notation was given by Landau, okay, so in around 1800 something. So f of x is said to be big O of gx if there exist constant c and k such that absolute value of f of x cannot exceed c times absolute value of g of x whenever x is greater than k. So as x is approaching towards infinity, means is going away from k, absolute value of f of x is less than or equal to c times mod of g of x. C is known as Borel constant, as I told you in the last class. Borel constant, okay. So I gave you a couple of examples, and I think today I'm going to do a few more examples. So first of all, now I would like to give you one example that we need to show that, and again I am mentioning that all these examples are from the book. I'm just following your textbook so that you have some synergy with there. Show that n square is not equal to big O of n. Okay. So that means what we need to show? We need to show that no pair of constants c and k exist such that n square, since n is positive, so absolute value we are not writing, right, less than or equal to constant times n, c times n, whenever x is greater than k, right? So we need to say that, we need to show that no pair of such constants c and k we can find such that whenever x is greater than k, n square is less than or equal to cn. So observe that if this happens, suppose this is true, so when n is positive, right, n square less than or equal to cn will imply that n is less than or equal to c, because we can cancel n on both sides, right? And so this implies that n is less than or equal to c whenever x is greater than, sorry, this is n, I'm sorry, this is n, okay, yeah, whenever n is greater than k, right? So now on one side n is less than equal to a fixed quantity, on the other side n is more than a fixed quantity. This is a kind of a contradiction, contradiction. So we cannot find such constants c and k. So n square is not big O of n. Okay. Let us take another example. So we know that 7x square is big O of x cube. This we saw in the last class, that 7x square is big O of x cube. So we can find constant c and k such that 7x square is less than or equal to c times x cube. Okay. So remember, whenever x was greater than, say, so k was 7 here in the last class. So one can ask a question, Is it true? The reverse is true, means x square is big O, x cube is big O of 7x square. Can I say that? Okay. Is it possible? So again, we need to find constant c and k and c such that x cube is less than or equal to c times 7x square, right? Okay. Whenever x is greater than k, we need to find constant c and constant k such that this happens, right? So from here, for every x greater than k, we know that we can cancel x and we will get x is less than or equal to 7 times c, right? We can cancel x square on both sides, right? For every x greater than k. Again, there is a similar situation in the previous example, that x is going away from a fixed quantity and x is bounded by a fixed quantity. This is not possible, right? So no such c and k exist, right? This implies that x cube is not equal to big O of 7x square. Okay. Okay. Now there is a very standard result in terms of polynomials. So I would say that it is a kind of a property. If f of x is a polynomial like a n x raised to power n plus a n minus 1 x raised to power n minus 1 plus dot 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 a1 x plus a naught, where these coefficients ai's are real numbers. Okay, all these coefficients are real numbers. Now I would like to show that f of x is big O of x raised to power n. So whatever is the highest power here, you see function f of x is big O of x raised to power n always. Proof is fairly straightforward, but let me give you the proof. So absolute value of f of x will be what? Absolute value of a n x raised to power n plus a n minus 1 x raised to power n minus 1 plus dot 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 a1x plus a naught, absolute value of these things, right? Now we know that triangle inequality, that mod of x1 plus x2 is less than or equal to mod of x1 plus mod of x2, or if there are three numbers like mod of x1 plus x2 plus x3 is less than or equal to mod of x1 plus mod of x2 plus mod of x3. So in general, if there are n numbers, so basically then we have mod of x1 plus x2 plus x3 plus dot 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 xn is less than or equal to mod of x1 plus mod of x2 plus mod of x3 and so on, right? So basically this whole quantity will be less than or equal to, by triangle inequality, for n things, mod of a n x raised to power n plus mod of a n minus 1 x raised to power n minus 1 and so on, mod of a1x plus mod of a naught. Okay, by triangle inequality. Okay, so now so let me rewrite it here. So mod of f of x is less than or equal to, I will take x raised to power n common, so we are left with mod of a n plus mod of a n minus 1 divided by x plus dot 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 mod of a naught divided by x raised to power n. Right, I have taken x raised to power n common. You can see that if I take x raised to power n common from whole thing, so here it will be 1 by x, next term it will be 1 by x square and so on. Finally, mod of a naught divided by x raised to power n. Right, now whenever x is greater than 1, so we know that when x is greater than 1, this implies that 1 by x is less than 1, right? And so on from here. So 1 by x is less than 1 and so on, 1 by x square is less than 1 and so on, right? So basically we are left with This whole quantity is less than or equal to x raised to power n times mod of an plus mod of an minus 1 plus mod of a naught. Okay. So that means this is our new constant c, and this is true whenever x is greater than 1. So we have constant c is equal to summation I is equal to 0 to n mod of ai, and constant k is equal to 1. So for these two constants c and k, we know that f of x is big O of x raised to power n. So very important result, very useful result. So whenever there is a kind of polynomial, we are going to do this. Okay. Next example. Show that 1 plus 2 plus 3 plus dot 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 up to n is big O of n square. So essentially, one way of looking at it, you know that sum up to n numbers. So we can always attempt these problems in a different way. So for one way will be, because we know that 1 plus 2 plus 3 up to n, sum of n terms is n into n plus 1 by 2, right? So n into n plus 1 by 2 is nothing but n square plus n divided by 2. So now again you see again the kind of polynomial you can use. So basically, you know everything will constant will be absorbed in big O notation. So everything is also order of n square. You can directly see that. Otherwise also, we can say that 1 plus 2 plus 3 plus n is less than or equal to, we know that 1 is less than n always, right? 2 is less than n, 3 is less than n. So this is less than or equal to this, which is nothing but n square, n times, right? So therefore, when constant c is equal to 1 and k is equal to 1, so basically for n greater than 1 we are saying. So this whole quantity is that 1 plus 2 plus n is big O of n square, right? This is easy to show. Now let us take some more examples. Okay. Factorial n, I think this is a very popular result. Factorial n is big O of n raised to power n. Okay, and the proof is very simple. How? We know that factorial n can be written as 1 into 2 into 3 into dot 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 n, right? Now again, for n greater than 1, if n is greater than 1, right? So this whole quantity will be less than or equal to n into n. So 1 is less than n, 2 is less than n, 3 is less than n, and so on n, right? The product of n times this is nothing but n raised to power n. Therefore, for c is equal to 1 and k is equal to 1, because n is greater than 1, this is our k here, right? And c is 1, right? We arrive at that factorial n is big O of n raised to power n. So in fact, from this expression, I can arrive at a couple of other expressions. If I take log on both sides, so log of factorial n is less than or equal to n log n, right? If I take log on both sides, because right hand side it is n raised to power n and left hand side is factorial n, so log factorial n is less than or equal to n log n. So again, for c is equal to 1 and k is equal to 1, because we are taking n is equal to greater than 1, this shows that log of factorial n is big O of n log n. This is also a very useful result. Many times while calculating the complexity of algorithms, you will arrive at that log of certain thing is, log of factorial n you need to compute. So we know that now it is big O of n log n. Okay. Another example, we know that I mean, n is less than 2 raised power n when n is a positive integer, right? I mean, n is greater than 1. In that case, we know this inequality holds. By the way, if you want to know more, learn about inequalities, probably in your IIT JEE exam, you might have, there is a book by G.H. Hardy. It's a very famous book. If you want to learn more about inequalities, by G.H. Hardy. So this inequality will hold anyway because this is a power, right? So this will be bigger than this whenever n is greater than 1. So again, for c is equal to 1 and k is equal to 1, because n is greater than 1 we can take, right? So this whole, we can say that n is big O of 2 raised power n, right? Again, from this, if I take log on both sides, and that log of base 2, so we will have log 2 base n will be less than n, right? If I take log base 2 on both sides, so this will be n log 2, which is 1, right? So this is n. In other words, for c is equal to 1 and k is equal to 1, log 2 base n is big O of n. That's another useful result, that log 2 base n is big O of n. Okay. Now, actually, I can use this result. So actually, I will use this result again to arrive at another result. This is for base 2. If I want to estimate log of any base b also, so what will happen? So I'm asking what happens to log b base n. Now log b base n is nothing but log at base 2 of n divided by, I can say log at base 2, right? And so this log 2n is less than n divided by log 2 base b, because log 2 base n is less than n, right? So log b base n is less than n divided by log 2 base b. So therefore, when constant c is equal to log 2 base b and k is equal to 1, we can say that log b base n is big O of n. That's another important result, that log of any base b is big O of n. Okay. Any question at this point? So these are some easy things, right? Okay, fine. If there is no question, so we can proceed. Now I can try to find a sum formula for the big O notation. It is known as sum formula. So if f1 of x is a function which is big O of g1 of x, right? And f2 of x is a function which is big O of g2 of x. Okay. Then the sum function f1 plus f2 of x is big O of maximum of mod of g1x and g2 of x. Okay. So we can prove this simple thing, and I think while computing the big O for various expressions, we use this formula quite often, So let us try to prove this. proof is not very difficult. From the first expression that f1 of x is big O of g1 of x, we know that by definition that mod of f1 of x is less than or equal to some constant c1 times mod of g1 of x, right? Whenever x is greater than k1. And the other expression, this will give us that mod of f2 of x is less than or equal to some constant c2 times mod of g2 of x whenever x is greater than k2, right? Now that means we have f1 plus f2 of x. In fact, I can go to the next page. So mod of f1 of x is less than or equal to c1 times mod of g1 of x whenever x is greater than k1, and mod of f2x is less than or equal to c2 times mod of g2 of x whenever x is greater than k2. Now I look at this expression and see what happens. So now f1 plus f2 of x is nothing but, so we can say that actually I can just look at the mod of this whole thing, right? So mod of f1 of x plus f2 of x, right, is less than or equal to mod of f1 of x plus mod of f2 of x by triangle inequality, right? Now this quantity is, the first quantity is less than or equal to c1 times mod of g1 of x, right? And second quantity is c2 times mod of g2 of x. When we are combining, x is greater than both k1 and k2. Remember, for the first expression, it was greater than x is greater than k1. For the second expression, x was greater than k2. So this inequality will hold whenever x is greater than both k1 and k2. Then this will hold, obviously, right? So the whole thing is less than or equal to c1 times, I can give a new name, mod of gx plus c2 times mod of gx, which is nothing but c1 plus c2 times mod of gx, or this is some constant c times mod of gx. What is gx? Gx is nothing but maximum of mod of g1x comma g2x, right? So for constant c is equal to c1 plus c2 and x is greater than maximum of both k1 and k2. So our this is nothing but k. So for k is equal to this quantity, maximum of k1 and k2, c is equal to this quantity, we have shown that absolute value of f1x plus f2x is less than or equal to c times mod of gx, right? So that means our inequality is satisfied. So we know we have found the value of c and k, right? So our addition formula works. So f1 plus f2 of x is big O of maximum of mod of g1x comma mod of g2x. Just like that, for sum there is a result, there is also a result for the product. So now we are writing it for product. Okay. If f1 of x is big O of g1 of x, okay, and f2 of x is big O of g2 of x, then f1 f2 of x is big O of g1 of x into g2 of x. Okay, for the product is straightforward. So in fact, the proof is simple. Just we compute mod of f1 f2 x, right? So this is equal to mod of f1 of x times mod of f2 of x, because mod of x1 x2 is equal to mod of x1 into mod of x2 by formula. And this is less than or equal to c1 times mod of g1 of x times c2 times mod of g2 of x. The whole thing is less than or equal to, I am just applying these two results. From here, mod of f1 of x is less than c1 times mod of g1 of x, and from here, mod of f2 of x is less than c2 times mod of g2 of x. The whole thing is less than or equal to c1 c2 times this, right? Which is nothing but less than or equal to c1 c2 times mod of g1 g2 x, right? So our constants, new constant is c, and our k is again, as usual, maximum of both k1 and k2, right? So from here, you remember that mod of f1 of x is less than or equal to c times mod of g1 of x, where x is greater than k1, and from here, mod of f2 of x is less than or equal to c times mod of g2 of x, where x is greater than k2, right? So combining these two results, we arrived at, when k is this and new c is this is our c and this is our k, our job is done, right? So now let me use these results. I mean, you can use these results, or otherwise directly also you can find, you can solve some results. So let me do some more examples. Show that f of n is equal to 3n log factorial n plus n cube plus 3 log n. So show that this whole quantity is big O of n square log n. So now you see that for each individual thing I know. So for this one I know that n is order of what, log factorial n is order of n log n, you know, this is order of n cube, and so on. We can combine them and add them. So for product and then sum, and we can compute this, right? So anyway, so let us see this. I mean, there is no hard and fast rule that you are going to use the same formulas, but anyway, it's up to you how you want to show this. Log of factorial n is n log n from the previous result, right? And we know that 3n is big O of n. So any constant is absorbed always in big O notation, right? Therefore, 3n log factorial n is big O of n square log n, right? By combining using the product rule, right? Is this. Now, to look at this part, n cube plus 3 is less than 2n square whenever n is greater than 2. This again you can prove it as inequality, right? So this implies that in fact if I multiply both sides by log n, you know, we will arrive at that, you know, what, n cube plus 3 times log n less than or equal to 2n square times log n. And so for c is equal to 2 and k is equal to 2.
Sir,
Yes?
sir, how this will hold true for all n greater than 2? This n cube plus 3 will be less than 2n square.
Yeah, so to
That
prove
is
it, you know.
not.
That's not satisfying, sir.
Yes, sir.
Okay. So I think check if it is true, or if it is not true, then I think you know, you can try to do it with some other values also, you know, some other things.
Sir, we can check at n equal to 5 or 6 or something like that. It is not holding true.
Yes, it's not holding.
So if
Sir, instead we can use 2n cube.
Then
so
the
two-
order will not be
then we will have a bigger
big of
order,
n
basically
cube.
bigger order. Yeah, so I think n cube plus 3 is not giving us, 1 minute, let me see. So here I think, yeah, so you are right, actually this is not going to work, right?
Yes, sir.
So that is some problem. Oh,
N-cube
sorry. This is,
okay.
I am sorry. I made a mistake. This is n
Next
square.
question only.
This is n square. I made a mistake actually. This is n square plus 3. Okay. Now it is okay. Now it is okay. You got it?
Yes, sir.
Yes, sir.
This is n square. You are right. I made a mistake. I'm always right. So this is n square plus 3. So n square plus 3 is less than 2n square, right? This is true, right? Whenever n is greater than 2. This is n square plus 2. Okay. So n square plus, 2 is this. So that means n square plus 3 times log n is big O of n square log n, right? Fine. So now this quantity is big O of n square log n, this quantity is big O of n square log n. So overall the whole quantity f of n will be big O of n square log n. Got it? This is n square plus 3, yeah. Okay, so this is one result. Now let us do the other part. Another example. Is it clear, right? There is no doubt in the previous example, I hope, right? Okay, now
Yes, sir.
yeah, okay, fine. Now let us look at example. F of x is equal to x plus 1 log of x square plus 1 plus 3x square. Show that this is big O of x square. Okay. So again, x plus 1, this, if first we focus on the first quantity, this one, x plus 1 is big O of x, right? This we can show because, so essentially if there is a constant here, so this is absorbed in big O, right? Okay. And now we look at x square plus 1. Since x square plus 1 is less than or equal to 2x square, whenever x is greater than 1, right? Because this is x square plus x square, right? So, therefore, log of x square plus 1 less than or equal to log of 2x square, which is nothing but log of 2 plus 2 log of x, right? Which is less than or equal to 3 log of x. Okay. So log 2 is less than log x and log x is less than 2 log x. So overall is less than or equal to 3 log x. Okay. Therefore, for x greater than 2, log of x square plus 1 is equal to big O of log x. Okay. Therefore, when we multiply with x plus 1, because we know that this is big O of x, the whole thing is, therefore, we have by the product rule x plus 1 times log of x square plus 1 is equal to big O of x log x, right? By the product rule. This x plus 1 is big O of x and this quantity is big O of log x. So the product will be big O of x log x, right? Now the other part, 3x square. So we know that 3x square is big O of x square because, constant is absorbed always. So it is big O of x square. So therefore, fx will be order of maximum of x log x, which is this quantity, and x square, which is this quantity for the other one. So we have an estimate here, we have an estimate here, right? Now, which one is bigger out of these two? So we know that for x greater than 1, x log x is less than or equal to x square whenever x is greater than 1. If this is true, that means the whole quantity f of x will be maximum of this, which is big O of x square. Got it? Okay, so any question up to this point? Any question after this point? Fine. So now I think what I talked about is a big O estimate, So basically, we know that f of x is big O of g of x if mod of f of x is less than or equal to constant times mod of g of x whenever x is greater than k, right? So this was an upper estimate. Similarly, we can give a lower estimate, right? So which is known as big omega notation. Big omega notation. So again, in the similar manner, f and g are functions from either integers or reals to reals. They want to be anything. F of x is big omega of g of x if there exist positive constants c and k such that mod of f of x is at least c times mod of gx. This time you see this inequality is reversed whenever x is greater than k, right? Then we say that f of x is big O. So it's a lower estimate. Okay. So example. Sorry. Sorry. Anyway, example is f of x is equal to 8x cubed plus 5x square plus 7. So we can say that this is big omega of x cubed. This is our gx actually. How? Since 8x cubed plus 5x square plus 7 is at least 8x cubed, right? Because there are more terms here, right? For every positive reals. Therefore, g of x okay. Sorry, not g of x. So this is how it's a big omega, right? Now, there are some standard reference functions which are quite often used. We compare the functions or find out the estimate from some standard reference functions. These are power of x, n is positive, or c raised to power x when c is positive. Okay, we sort of compare it with these functions. Now, another thing is big theta function. If again f and g are functions from integers or reals to reals, right? We say that f of x is big theta function of g of x if two things happen. F of x is big O of g of x, upper estimate, and f of x is lower estimate also by the same function. Okay. Then we say that f of x is theta of g of x. And again, I should mention that some reference functions here that we use are x raised to power n, c raised to power x when c is positive, log x, and so on. Okay. Let us do some more examples. Now, 1 plus 2 plus 3 plus n. we saw that 1 plus 2 plus 3 plus n is big O of n square, right? We know that this thing is big O of n square, right? We saw that recently. Now I would like to show that we also have that 1 plus 2 plus 3 plus dot 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 n is big omega of n square. How? So let us write down 1 plus 2 plus 3 plus dot 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 n. Now I am going to ignore out of this expression, half of them I am going to drop, and I am going to count whatever is left from n by 2. So kind of middle of things, right? So this will be mod of n by 2, then plus mod of n by 2 plus 1 plus dot 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 n. So basically, why this quantity is bigger than this quantity? From this expression, from this sum, I have dropped first half of them, right? So whatever is the thing. So if n is 16, I am dropping first 8, and then next of the 8 are written here, right? That's what I am doing. So, or that's why we have put, because this could be even or odd, the mid could be. So I am writing this function here. Okay. So after ignoring first half, I can write this inequality, right? This whole quantity is this. So this means this whole expression is less than or equal to, now this n by 2. Now this is also bigger than n by 2, and all other expressions will be bigger than n by 2. Finally, I can write down this, right? So whole quantity will be, now this is expression is nothing but n minus n by 2 plus 1 times n by 2, right? So the whole quantity is less than or equal to n by 2 into n by 2, which is n square by 4. So 1 plus 2 plus 3 plus dot dot n is big omega of n square. Again, the constant c is equal to 1 and k is equal to 1. Okay, for the same thing. Now, since we have this and this both together, remember, if we have f of x equal to this and f of x equal to this, that means we have f of x equal to theta of g of x. So in other words, we can write down that 1 plus 2 plus 3 plus n is big theta of n square. This is a important result. Okay. In fact, I should mention that sometime it is easy to write down f of x is equal to big theta of g of x if there exists constant c1 and c2 such that c1 is mod of g of x less than or equal to mod of f of x. This is obvious from the definition, c2 times mod of g of x whenever x is greater than k. So this means actually this, right? This portion gives you that f of x is, so one portion gives you, so this portion gives you f of x is this lower bounded by, and the other portion gives you f of x is big O of g of x. Okay. Okay, let me do one more example. Three x square plus 8x log x is equal to theta of x square. Okay. So we know that 0 less than or equal to 8x log x is less than or equal to 8x square. Right. So therefore, 3x square plus 8x log x less than or equal to 11x square So for x greater than 1, I am taking, right? So therefore, 3x square plus 8x log x is equal to big O of x square. Okay. Now we know that x square is, so basically this is big O of x square. Now show that this whole thing is lower estimate. I think I'll just leave it as an exercise for you now, just to see that this happens, Anyway, now now the important thing is that why we are doing all this big O notation, big theta notation, big omega notation, to estimate the complexity of algorithms, right? So this is a very important topic when we want to implement some, suppose we want to do some task, okay? If the complexity is polynomial time, I mean is bounded by a polynomial, right? A big O of x is for n or something like that, then we can implement it easily, we can efficiently solve. But if it is exponential time, it is difficult to implement, right? So I think these kind of estimates are quite useful, so one very nice thing is that, so I think let me talk about computational complexity a little bit. So computational complexity is of two kinds. One is time complexity and the other one is space complexity. Okay, so time complexity means number of operations used by the algorithm when the input has a particular size. And in fact, we are going to focus more on time complexity. The space complexity is similarly, when we measure the space. So I leave that right now. We focus on the time complexity. So number of operations used by the algorithm when input has a particular size. So let us take an example. So you remember we had a problem that a1, a2, and integers were given to us, and you have to find the maximum element. This we have done the algorithm in the last class. Find a maximum element. That algorithm, what we were doing, if I have to find the time complexity, I have to find the complexity of this algorithm. Note that what we were doing here, for each I, if you remember, for each I from 1 less than equal to I less than equal to n minus 1, because we were running from 2 to nth element, second element to the nth element, right, in the algorithm. And for each I, we were making two comparisons. Right, one to determine the end of the list, whether we reach the end of the list, and the second comparison was, updating the term or not. Right, or not. If maximum is found, right, I mean, we were just updating, the term, right? So these two comparisons we were doing for each I. That means, and then actually one comparison was to exit the loop. To exit the loop. So total number of comparisons, if I count, it will be total number of comparisons is equal to 2 comparisons for each such a thing n minus 1. So 2 times n minus 1 plus 1 comparison to exit the loop is this quantity. And I think you can easily show that this is nothing but big theta of n, right? This whole quantity is big theta of n. So this is a, you know, nice thing to do. It's a straightforward thing to do. Now, you know, if I ask you another example, linear search. The problem was A1, A2, and integers were given, and you have to search for x in this, right? Where is x? So as you know that, again, I think I leave it as an exercise for you to show that locating one object. So the worst case complexity is big O of n. Okay. So worst case complexity is big O of n. So basically, out of n objects, you have to find one object. The worst case complexity is big O of n. This you can actually verify again, you know, by looking at the algorithm that we discussed in last time in the class. So you need to look at each step of the loop in the algorithm, how many comparisons we are doing, right? Okay. So, you know, again, in the similar way as we have done for the previous example, one comparison you need to do to see the end of the reading, end of the list, and one and the other comparison will be compare x to the term, if it is equal to whatever you are looking for or not, right? So if x is equal to ai, so then total 2i plus 1 comparisons you are doing, right? And one comparison to made outside of the loop, right? So, you know, basically depending upon whether x is in the list or x is not in the list, you can count how many comparisons are there, you know, in the algorithm. So I leave it as an exercise. You can see that it is worst case complexity is order of n. I should mention here that if you want to search for one object out of n objects, so this worst case complexity is order of n. But on our classical computer, but for a quantum computer, this is big O of square root of n. So that is much faster algorithm on a quantum computer. So that's why quantum computers are quite useful. So I think that's all for today. If you have any questions, please ask. So next class we will be starting counting, you know, the other chapter. So we have covered big O notation, some algorithms, and so on. Yeah. So chapter 3, some portion we have covered. This is all chapter 3 in your textbook. So please do read your textbook, and if you have any questions, you can ask. Otherwise, I can stop the session.
Hello, sir.
Yes.
Sir, is there is always exist a big theta notation for any function?
I mean, you can always estimate upper and lower bound, right?
Yeah.
Yeah. So basically, you know, if you want to know more about this order, so as I told you, so the very good book is Order of Infinity by G.H. Hardy. Very good, very famous book. Maybe you can buy it or something online. G.H. Hardy, very beautiful book. But you know, this is purely mathematical. But if you want to look at computer science perspective, I would say that then you look at this book by Knuth, you know, because Knuth has popularized these things in computer science, art of computer programming by Donald E. Knuth. Right. So please do look at this book. It's very, very important, you know. So you see that he has given, as I told you, there are 15 different sorting algorithms he has given, you know, searching, sorting. These are very common tasks that you do as a computer scientist. So you should know what are the best algorithms, you know, for doing a task. If I ask you do some problem, so you know that okay, which algorithm should I choose. One very important thing about the complexity is this, that suppose you are working in a company and your boss says that, you know, do this task, you know, they don't understand any complexity, you know, they will say that probably it is easy. So if you can show to them that, well, it is very, very difficult, you know, in fact there is something called as NP hard problems, which I have not discussed it here. So you say that the problem is NP hard, so that means it is very difficult, so nobody will be able, so you say that nobody will be able to solve, neither me or no anyone else can solve this problem. So then we go about the approximation algorithms and so on, you know, all kind of different things are there, you know, in computer science, but that you will read at the advanced level. But you know, so but the complexity is very, very important, you know. So before implementing a computer program for a given problem, you should know what is the complexity, and if there are better algorithms known for doing the task. So actually there is a book by you know, David Johnson, a very nice book on this class P and class NP problems. There you can find a lot of this stuff. Again, that's an advanced course, you know, you will be doing in computer science. Or you know, there is a Scott Aston has given a you know, complexity zoo on the web. You can find out complexity zoo, all different classes, you know, by making. So actually I should tell you, if you can solve a problem in polynomial time on a deterministic Turing machine, it is known as class P problems. If you can solve the same problem in polynomial time on non-deterministic Turing machine, so basically then it is known as you know, you know, basically, so one is a, so basically given a problem, if you can solve in polynomial time on deterministic Turing machine, so this is class P problem. If you solve on a non-deterministic machine, it is known as class NP problem, right? So these two kind of problems are there, and there is a big question whether P is equal to NP or not. You know, $1 million has been announced. This problem is still open. So a lot of interesting things are there in this complexity, you know. You know, so you can find out these things on the internet. Any more question?
Yes, sir. Sir, n factorial, Big-Theta notation of n factorial will be n raised to n. Big-Theta notation of n raised to, or n factorial will be n raised to n.
Yeah, so just do, actually, you know, do the calculation. Don't ask me, just try and do. Okay. So all this discussion you can do on the WhatsApp group, you know, just discuss and let the other also comment. I think in the WhatsApp group there is not much discussion going on. In fact, you know, I think I would encourage such kind of things on the WhatsApp group, right? Let other comment. Okay. Yeah. So
Okay.
just, yeah.
And sir, what about project? Means that
Yeah. So I think actually, yeah, I could not discuss with our Professor Rahul Mattu. So I think today I will be discussing it, and then probably I will be posting it. We will be posting it, right? So we have to synchronize with both the sections. Yeah. So we will be doing that actually. Okay.
And sir, tutorial has not uploaded. Means for
Yeah.
test.
So I think they were working on it. I will check with them. You know,